bigger and bigger and bigger and bigger. Wouldn't it be great if our height grew exponentially? I mean, we'd be the height of the Eiffel Tower in no time. In that case, our height would be following a geometric sequence. Let's explore geometric sequences in this video. Okay, so a geometric sequence is a sequence of numbers with the same ratio between consecutive terms. So, exponential, just like my height is growing in a geometric sequence. In general, the terms of a geometric sequence we represented this way: g1 through gn, where r is the common ratio and n is the number of terms. And look here, this is an example of a geometric sequence because the common ratio is 2. We're always multiplying by 2 for every term. And it can also have a negative common ratio or a ratio that's fractional. So it could be something like this: 1/3, 1/9, 1/27, so on. So if you have a geometric sequence and you know the first term and the common ratio, you can calculate the nth term. So let's say something like this. To find the nth term, you just multiply the first term by the common ratio to the power of the number of terms minus 1. So essentially what that's doing is, let's say you know the first term, you're trying to find the 10th term, and you know the common ratio is 2. You're trying to multiply the first term by the common ratio to the power of however many terms are in between the first term and the last term, which is n minus 1. In this case, 9. And that's where this formula comes from. And also, like, you can express it in terms of other terms. So let's say you know the fourth term is 36 and you're trying to find the ninth term where the common ratio is 3. Then you would just do 36 times 3 to the 5 because there's 5 terms in between the fourth and the ninth term. So you multiply by 3 5 times. And that's essentially what this is saying right here. Okay, cool. And this is not that important for the sake of AMCA. So let's move on to the sum of all the terms in a finite geometric sequence. Okay. So essentially, all we have to do is to find it is to do the first term, which you can say g of 1, times 1 minus r to the n over 1 minus r. Or another way of putting this that's oftentimes more helpful is the first term times r to the n minus 1 over r minus 1. The easy way to remember it is r to the n minus 1 over r minus 1. Numerator, denominator, they're so close, but the only difference is r has a power of n in this case. And then you, of course, will just multiply by the first term. And we'll come back to this one later. Let's first look at this problem over here. Okay. Call a 3-digit number geometric if it has 3 distinct digits. When read from left to right, form a geometric sequence. Okay, interesting. Find the difference between the largest and smallest geometric numbers. Let's take this one step at a time. Smallest. Okay. 3 digits. They form a geometric sequence. Remember, when you're trying to make a number as small as possible, the first digit matters much more because they're worth 100 instead of just 10 or 1. So what is the smallest possible value for the first digit? 1. Okay, so we've minimized the first digit now. It's the smallest possible. Now what is the smallest possible value for the second digit? Remember, it says 3 distinct digits, so we can't just make this another 1 and then have 1, 1, 1. No, that's not allowed. So in order to make this smallest number, we need to multiply it by our common ratio that's as small as we can get. The smallest number that's, of course, not 1, that can be a common ratio, 2. So 1 times 2, 2. And it's a geometric sequence, so we multiply by 2 again to get the third digit, 4. And this is the smallest possible number because the first digit was as small as possible and the ratio was as small as possible. Smallest number, 1, 2, 4. Largest number, a bit more tricky, but we can still handle it. Largest number, 1, 2, 3. Again, first digit matters the most. What should we make the first digit? Let's make it 9. Okay, this is a little bit tricky here. The common ratio. So notice how in the first one we have to multiply by something that's an integer. We can't multiply by half, right? 1/2, 1/4, that's not a 3-digit number, is it? But in this case, we cannot multiply by something like 2 or 3, because then our digit would be 18 or 27, which is not allowed for a digit, right? Digit is 0 to 9, not 18 to 27. Okay, so we have to multiply by a fraction, but we still have to keep this digit an integer. Digits cannot be fractions, of course. So what are some possibilities? Can we multiply by half? No, 9 isn't divisible by 2. What about a third? Yeah, that would work. So one possibility could be 931. A ninth, that wouldn't work because 9, 1, 1/9. Okay, so we have one possibility. Is this really the largest? Remember, we're trying to maximize these two digits. This one is already as high as it can get. Is there anything a bit bigger? Okay, so remember, 9 is 3 squared. So the fraction we're multiplying it by has to be, it cannot, basically it must keep the term 9 times the fraction in integer. So let's write this as 9, let's say 9r and 9r squared. R is a fraction, right? And we know 9r squared must be an integer, and we know r has to be less than 1. Right? We can't just make this 9 because that violates the basic condition of the problem, and it can't be more than 1, like I mentioned earlier. It has to be less than 1. So is a fraction less than 1? Notice here, 9r squared is an integer. 9 is 3 squared. So that means that 3 squared r squared is an integer, or 3r is an integer. So that means r has to have a numerator, has to have a denominator of 3. So it has to be 1/3, 2/3, or something like that, right? Because anything else, let's say it was 2/5. If r was 2/5, now this is not an integer. But remember, we want 3r to be an integer, so this won't work. So the denominator of the fraction, the common ratio, it has to be 3. So basically our only two possibilities are this. We've already seen this. What about this possibility? That gives 9. 9 times 2/3, 6. 6 times 2/3, 4. That works, and that's even bigger than 931. So really, our largest number is 964. We're asked to find the difference, so 964 minus 124, 840, our answer. So to summarize the key ideas in this problem, to do this, basically we look at the smallest and largest separately. Smallest, 1, 2, 4. We found that pretty easily. Largest, 964, by seeing that we must have 9r squared be an integer, because all digits are integer, which means 3r is also an integer, but that means r has to have a denominator of 3 or 1, but you can't have a denominator 1 in a fraction, so the denominator was 3, two possibilities. This one's larger, so 964, and we subtract and get 840. Let's try this problem over here. Suppose n is a positive integer, and d is a single digit in base 10. Find n if n over 810 equals 0.d25, d25, d25, so on and so forth. And to explore this, remember I skipped this formula earlier. Here's a good formula for the sum of terms in an infinite sequence. So let's say we have a sequence like this. 2 plus 2/3 plus 2/9 plus so on. So it's infinite sequence. It doesn't just end like that. The sum is the first term over 1 minus the common ratio, which is 1/3 in this case, right? Times 1/3 times 1/3. So this is equal to 2 over 2/3, 3. So the sum is 3. And this only works if the common ratio is greater than -1 and less than 1. Because if you have something like this, forever, it's going to be equal to infinity, right? Just keep multiplying over and over. And this is something else, we're not going to explore it. But just remember, the common ratio has got to be less than 1 and greater than -1. So now with that in mind, let's see if we can tackle this problem over here. Okay, this is interesting. So D25 is a repeating decimal. Let's express this in terms of fractions. D over 4. Let's do this. 100D plus 25 over 1,000. What is this? This is basically 0.D25, right? This is D25, the number, which is 100D plus 25 over 1,000. So that's this part over here. And then we add that to, let's say, 100D plus 25 over 1,000,000. And what is that going to be? 0.000D25, right? That's going to just be this expressed in base 10 notation. It's 100D plus 25. If you imagine it's D25 is 100D plus 25, and then we're shifting the decimal point 6 places left, so divided by 1,000,000. Now, we can keep going on again. 0.00000D25. This is again 100D plus 25, which is the simple expression D25 over this time. We're shifting the decimal point 9 places left, so over 10 to the 9. Interesting. So from here, let's it's the same thing. The expression we're dealing with seems very similar, right? This is this part over here. This is this part over here. This is the next part over here, this one. It seems like we can express this quantity here as the sums of all its individual parts. This part plus this part plus this part, so on, which is nothing but this plus this over 10 to the 9, and so on forever. So let's simplify this expression over here. Let's first write it, 100D plus 25 over 1,000. Let's write it as 10 to the 3 because that's a little bit easier to deal with. It's much easier to say 10 to the 12 than saying 1,000,000,000,000,000,000,000, if that makes sense. So that's why we're going to convert it to power notation. So it's easier to say, right? And look here, it's the same term except we're dividing by 10 to the 3 with each term. It's the same term except the denominator is 1,000 times bigger, 10 to the 3 times bigger. So this expression would then be nothing but a, the first term, over 1 minus the ratio. And the ratio is just 1 over 1,000, right? Because we're multiplying by, the denominator is getting 10 to the 3 times bigger every single time. So it's the same thing as having a common ratio, 1 over 10 to the 3, or 1 over 1,000. They're the same. And now we just simplify this, 100D plus 25 over 10 to the 3 over 10 to the 3 minus 1 over 10 to the 3. Cancel out the divided by 10 to the 3 terms to get 100D plus 25 over 10 to the 3 minus 1, which is 999. And let's get out of the way. And we know this quantity is equal to n over 810. Okay, so now we know d is a digit, so it can't be like 20 or 30 or whatever. And n is a positive integer, okay. Already here we've got some common terms we can just divide out, So 100D plus 25 over 111 equals n over 90. And then you can cancel out another factor of 3. Get this, and 100D plus 25, remember, is just going to be d, where d is a digit. Now we have 30 times 100D plus 25 equals 37n. Aha, the right side is a multiple of 37, which means the left side also has to be a multiple of 37. So now we can just try all the values of d from 0 to 9, 25, 125, and remember, we need it to be a multiple of 37. Right side's a multiple of 37. Left side, we need 100d plus 25 to be a multiple of 37. 100, 125, 225, 325, 425, 525, and from here, we can notice that 525 is divisible by 37. Or actually, never mind. It turns out 525 is not divisible by 37. So, sorry about that. We can keep going. 6 or 625, 725, 825. Is 825 divisible by 37? No, 825 is not divisible by 37. Is 925 divisible by 37? Let's see. (925) is divisible by 37. Cool. So we can see from here that 925 works, so that means d equals 9 to make this 925. So our answer is just, find n. So if d is 9, then 30 times 925 equals 37n. So that means n is 30 times 925 over 37 equals 30 times 25, 750. And we are done. So our answer is 750. Let's summarize. First, we had to use a geometric sequence formula. Then we saw this must be true by doing some simple algebra. Then from here, we got this expression. And then from there, we saw this quantity must be multiple of 37. You can just try all of them and see that 925 is indeed divisible by 37. So d is 9, we plug that in, solve for n, get 750. Okay, now we're going to move on to this problem. Evaluate 1/2 plus 2/4 plus 3/8 plus so on. What is this? It's not a geometric sequence, right? Notice here, 1/2, 2/4. The denominator is getting 2 times bigger. But the numerator is also changing. That's strange. Look at this. So the denominator is getting 2 times bigger. And the numerator is also increasing by 1 every time. This isn't really an arithmetic sequence. It isn't really a geometric sequence. What is this? Well, it's an arithmetico-geometric sequence, which is a very cool and special type of sequence. So notice that it seems almost like a geometric sequence. If it was 1/2 plus 1/4 plus 1/8, then it would be a geometric sequence we can easily solve using the infinite geometric sequence formula. But it's not. But maybe we can make it something like that. So here's the cool part of the trick. Notice how 1/2 plus 2/4 plus 3/4, it's kind of like a sum of multiples. So the idea here is we're going to be expressing this as a sum of multiple different sequences. Right? This is dot, dot, dot. So let's break this down. So 1/2 plus 1/4. Let's try to make that top sequence over there. Let's try and make this top sequence by using other sequences. 1/2 plus 1/4 plus 1/8 plus 1/16 plus so on. That's one sequence. Okay, but look here. We're trying to form this sequence, right? And we've only got one copy of each term. Let's see what's missing. If we subtract these expressions, we get 1/4 plus 2/8 plus 3/16 plus so on. Interesting, but that looks like very similar to the original expression, doesn't it? Okay. Now we've got this thing here. Let's try and now we have this part left. How do we get this part? So now what we want to do is, whoops, in order to get that part over there, let's have another sequence. How about 1/4 plus 1/8 plus 1/16 plus so on. Now what's left? Now what do we have? Now if we, let's say, add up our two pieces, we have 1/2 plus 2/4 plus 2/8 plus so on. We're getting closer. We've got 1, 2. Well, we need 1, 2, 3, 4. Let's add another sequence. How about 1/8 plus 1/16? This is what we had earlier, right? Plus 1/30/32. Let's add that sequence now. We would get 1/2 plus 2/4 plus 3/8 plus 3/16 plus so on. We're getting closer. So it seems like we started with this original sequence. We then added this sequence. We then added this sequence. And it seems like we're getting closer to this sequence over here. Let's add another sequence. This time, 1/16 plus 1/32 plus so on. Now we would get this sequence. 1/2 plus 2/4 plus 3/16 plus 3/8 plus 4/16 plus 5/32 plus, oh, sorry, I'm blocking. 1/2 plus 2/4 plus 3/8 plus 4/16 plus 5/32 plus 5/64 plus so on. So now the idea here is that we can keep adding more and more of these subsequences to get our sequence, right? It's like we're kind of doing a pyramid kind of thing, if that makes sense. We're layering this. We've got 1 1/2, 2 1/4, 3 1/8, 4 1/16, and then we add another one, 5 1/32 terms, and so on. We're adding all the black box ones. So we just add an infinite number of such sequences. The sum of the first sequence, we can use the formula a over 1 minus r, or g1 over 1 minus r. We can use that formula over there to see that it's going to be equal to a 1/2 over 1 minus r, which is also 1/2. That is 1/2 over 1/2, 1. Cool. Now, what's next? The second sequence, 1/4 plus 1/8 plus 1/16. That's a 1/4 over 1 minus r, which is 1/4 over 1/2, because the ratio is 1/2. So the second sequence is equal to 1/4 over 1 minus 1/2, 1/4 over 1/2. That's 1/2. Interesting. So now what is the third sequence equal to? The third sequence is equal to an 1/8 over 1 minus 1/2, which is an 1/8 over 1/2, which is a 1/4. Wow. The next sequence will be equal to an 8. So it seems like each of these individual pieces we just added up, 1 plus 1/2 plus 1/4 plus so on. This is another geometric sequence with first term 1 and common ratio 1/2. So first term over 1 minus r, 1 over 1/2. The answer is 2. Wow. Okay, let's see another. So the idea here was to break it up into pieces. First you have this expression over here, then you have this part here, then this part here, and if you add an infinite number of these kind of sequences, we get this expression here. And then we evaluated each of them to get another geometric sequence. Let's explore another way to take a look at this problem. Let's call this sum S, right? So now what we can actually do is say divide its sum by 2. We get 1 over 4 plus 2 over 8 plus so on. And now what happens if we subtract s minus s over 2, we get that s over 2 equals half, right? Plus 2/4 minus 1/4, that's 1/4. Plus 3/8 minus 2/8, that's 1/8. Aha! This is a geometric sequence, and as we found earlier, its sum is first term over 1 minus r, just going to be half over half, 1. So from here, we also just get s is 2. Both are great ways to solve this problem, this one being a little bit more interesting. So the key idea was you divide by 2, and then you subtract, and then most of the terms cancel out. We're left with s over 2 equals 1, so s is 2. Now, we're going to move on to mean median mode, and it's related to sequences, but now the sequences are completely unordered. There's no pattern. And the applications can be very interesting because not all the time is it going to be as straightforward as just finding the simple formula. Let's explore that right there.